One thing we can do to solve this expression is to neglect this quantity, which is having a really small quantity h cross square. H, it's really it's Planck's constant, and h cross is h by 2 pi, and it's not widely different from that of h, and this is actually the square of that quantity, and it's going to be smaller compared to the remaining terms. So you can neglect this term and solve the remaining equations. So neglect terms of the order of h cross square. Then what you will be having is the remaining quantities, which will give you okay, so the first equation is going to be, when you are comparing the real coefficients, it's going to give you s prime square is equal to p square, which implies s prime is equal to plus or minus p of x, and this is also a function of x. So that is the first result you have. S prime is plus or minus px. Okay, so we will give some numbers for this equation. I think after 1 we haven't given anything. I need this expression, so I'll give this equation number 2, and this I'll give equation number 3. Now once you know s prime, you can find out s is nothing but ds by dx equal to plus or minus p of x, or s is going to be nothing but integral p of x, integral p of x dx plus or minus. So this is going to be your s. One thing that we wanted to calculate is s, so that is obtained. 4. Okay, now the second equation which is arising from that is 2s prime a prime by a, 2s prime a prime divided by a plus s double prime. S double prime is equal to 0. So from this equation, you can substitute the value of s prime here. S prime is nothing but p, so 2p a prime by a prime by a. Okay, I'll write this a prime like 1 by a, I'll write here, and a prime is dA by dx, plus here s double prime is nothing but dp by dx, which is equal to 0. Now to solve this equation, I will divide these entire terms by p. That will give you 2 divided by a dA by dx plus 1 by p dp by dx equal to 0. I can modify this equation in this form. So this is nothing but d by dx of log a. If you take the derivative, it's nothing but 1 by a dou a by dou x. 2 plus another term is going to be d by dx of log p, which is equal to 0. Okay, so both are d by dx term, you can write it together, d by dx of 2 log a plus log p equal to 0. This is nothing but d by dx of log a square p, which is equal to 0. Or this quantity is going to be some constant, and log a square p is a constant. A square p is also going to be a constant. A square p is another constant, which will give you a is nothing but some constant. I am taking this constant from constant as c, and by root p. So this is our quantity that we need to find out, the amplitude of our wave equation. So that is the fifth equation. Okay, so we found out s of x and a of x, and now we can write the complete solution of psi. So the psi of x in the general form will be some constant c divided by root p of x into an exponential term with I s of x, which we found as p of x, integrating over dx, and we have one explicit h cross over there. So this can have plus or minus solution, that is plus or minus, or you can split it and write for two different regime. So that is just a linear combination of the plus term plus the another term. That is going to be your wave function. Okay, we will write it, but while writing we will also incorporate the regions of the potential. So to show that, drawing the potential diagram once again, this is going to be the potential that some v of x. Okay, so as we discussed, this is the region, or classically allowed region. In this region you have your energy is higher than your potential. In this region you have your potential higher than energy. So depending upon the region, you will be having different solution for your psi of x. So we'll write for both the regions separately. So for classically allowed region, or when E is greater than V, our solution of psi of x is going to be of the form, you have this c root px sort of, and your amplitude is going to be raised to I by, exponential raised to I by h p of x dx. It's going to be a sinusoidal solution, as it is a classically allowed region. Or you can see that p of x definition, if you're seeing, that is nothing but root 2 m e minus v, and e minus v is going to be a positive term, and if that is the case, this is going to be a positive term, and the form is going to be like this, and some another. Okay, is a c1 and c2 root p of x e raised to minus I by h cross p of x dx. So that is for classically allowed region. Or classically forbidden region, again you have a wave function. For classically forbidden region, our solution is going to be of the form psi of x is equal to some another constant. Yeah, put the same constant. So here my p, the way I define p, is going to have an intrinsic minus sign, right? 2m e minus v is going to be having a minus sign. I will take a mod p of x to prevent that. Exponential, here again you will be having a minus sign which is coming out of it, so that will become it's p of x equal to root 2m e minus v, and when the minus sign coming out of the root, it will become I, and your I and I will cancel. That will become just an exponentially decaying term. So this will become something like e raised to minus 1 by h cross integral p of x dx plus some c2 root mod p of x e raised to plus one by h cross. Okay, so this is a final wave function for our two different regions. One thing you can observe here is the dependence of amplitude on the momentum. See, all these quantities, amplitude is depending upon the momentum. Inversely, right? Inverse root of that. So if you try to find out the probability of the particle at any instant, that is going to be proportional to 1 by p of x, or it's inversely proportional to the probability of finding a particle is going to be inversely proportional to the momentum. So this is something that is familiar for us from the classical examples of any problems which we have done in classical mechanics. The simple harmonic motion, for example. So if you take a simple harmonic motion, the particle will be executing motion like that. So at both the ends, the momentum is going to be minimum for the particle, and these are the locations where you are going to be seeing the particle most of their life while executing the motion. But this is a point where the motion is going to be really fast. The momentum here is going to be maximum, because potential energy is minimum and the momentum kinetic energy is maximum, and momentum is going to be maximum at this point, and that is a location where you are going to see the particle for the least time. So that is actually kind of a similar result that we have from classical mechanics. Another interesting thing about this WKB method is we have seen the wave function for classically allowed region, classically forbidden region. What about the boundary? What about these turning points? What is going to be the wave function at these turning points? So at the turning point, the momentum here is going to be maximum, and here it's going to be minimum or zero. It's returning from that point. So this is a point where your momentum is zero. What happened for the wave function when the momentum is zero? 1 by root of something, root 0, that will give you something like infinity, and the wave function is blown up there. That means you have a kind of a discontinuity at the boundary, and any point close to the boundary you'll not be able to get the solution by using this method. It is not continuous at boundary. So that is an important observation In fact, we can write it as a separate point that WKB approximation is not valid at the turning points. Classical turning points, I think that is the way we call it, turning points. Okay, so those are the main observation from this, and now what we have to do is we have to go to the validity condition of WKB approximation.